we have met two non-elementary types of differential equations. Firstly, so-called first-order linear differential equations. They can be written like this. So the derivative of your function plus some expression in terms of the variable times your function equals some other expression in terms of the variable. The key to solving a first-order linear differential equation is to write it like this and then multiply everything, let's say both sides of the equation, by the integrating factor, e to the power of capital A, where capital A differentiates to little a. Thereafter, you use the product rule backwards in the left-hand side. So this is the recipe for first-order linear differential equations. One remark is that the capital A is a function. Sometimes we write a as a of t, just to indicate that a is a function of the variable t. If t indeed is our variable. Here is a word problem which will boil down to a first-order linear differential equation. Suppose a population ft, which initially, that's to say at time 0, is 100 million, but we will just write 100 to keep the numbers smaller and nicer. Suppose this population has an upper limit of 300, and furthermore that the growth rate of the population is proportional to the deviation of the current population size to this upper limit of 300, as described in that the derivative of your population function, that's say the rate of change of a population, is 0.1, some number, times this deviation of the population from the upper limit of 300. And the task is then to find f of 60, let's say the population in 60 years' time. Okay, so we have a differential equation, let's solve it. This is a first-order linear differential equation, but when we apply the recipe, in which the first step is to identify what little a is, you must have the y in the left-hand side and the y prime coefficient must be 1. So let's make sure that these things are true for us before we apply the recipe. So that's why, to ensure that, I will move the function to the left-hand side, because now you can compare it with this one and see that little a is going to be 0.1. So let's write that little a is 0.1, and then capital A is going to be 0.1t, and e to the power of at is going to be e to the power of 0.1t. That's the integrating factor. Let's go ahead and multiply everything in our differential equation by the integrating factor. So we multiply also the right-hand side, of course, if we multiply the left-hand side by the integrating factor. Now, here's the nice thing. Now you can rewrite the left-hand side as this product by using the product rule backwards. Because by the product rule, the derivative of this is the third function derivative times the second function plus the third function times the second function derivative, and just use that backwards. But it's the recipe is always the same. You seem to always end up with a derivative of the function times the integrating factor. Now let's finish things off. So the derivative of something is 30 times e to the power of 0.1t. Then this thing has to be the integral of 30 times e to the power of 0.1t, because integration is differentiation backwards. If this guy differentiates to 30 times e to the power of 0.1t, it has to be the indefinite integral of 30 times e to the power of 0.t. That's the basic idea. And so this is 30, that just hangs around, times 0.1t divided by 0.1 plus c. Now let's get ft alone. So we divide by e to the power of 0.1t and we get 300 plus c times e to the power of minus 0.1t. So that's what a function must look like if it is supposed to satisfy the differential equation. Now we use the initial condition, which was given in words, that f of 0 was 100. Now we use that. So, you know, if we plug in 0 into our function, we get 300 plus c times 1. So that's supposed to be 100. And so c is seen to be minus 200. So f of t is 300 minus 200 times e to the power of 0.1t. And so answer, how many million people are there in the country at time 60? Well, it's f of 60, so it's 300 minus 200 times e to the power of minus 6. That is the value of f of 60, and that represents how many million people there are in the country after 60 years. With separable differential equations, you want to write the derivative in Leibniz notation. Then you separate stuff, you integrate, you make your function alone. If you also have an initial condition, you thereafter use the initial condition to determine the numerical value of your arbitrary constant. Here's a typical example. Find all functions y satisfying that its derivative should be 2t plus 1 all to the power 4 over e to the power 3y, and y of 0 is 35. First, you forget about the initial condition and focus only on the differential equation. First, you separate, so you collect all the y things on one side and the t things on the other side. Now you integrate. Dealing with the left-hand side is easy. What about the right-hand side? This is a little bit more complicated, but let's proceed with caution. If you started with 2t plus 1 to the power 5, you would use the chain rule to differentiate it. The 5 would jump down, then you would have times 2t plus 1 to the power 4 times 2, the inner function derivative. So to counter the 5 and the 2, we divide by 5 and by 2, and then plus c. Now we want to make y alone. So we can first, of course, move the 3 over to the other side, multiply everything by 3. Instead of 3c, I will just write a, because since c and a anyway are just arbitrary constants, why not be lazy and just write a? Basically, we can now say that 3y is ln of all of 3 times 2t plus 1 to the power 5 over 10 plus a, and then of course y must be a third of that. So this is basically what a function needs to look like if it is supposed to satisfy our differential equation. Here we have an arbitrary constant, as usual. Since we have an initial condition, y of 0 should be 35, we now use that initial condition to determine the numerical value of a for us. Now, on the one hand side, y of 0, so you replace t by 0, you get a third times lm of 3 times 1 to the power of 1 to the power of 5 over 10 plus a, and you wanted that to be 35. Okay, so lm of 3/10 plus a should be 105. And so 3/10 plus a needs to be e to the power of 105. Pretty big number, but the maths goes the way it goes. So a comes out as e to the power of 105 minus 0.3. So now we give our answer. So remember, y was a third ln of 3 times 2t plus 1 to the power of 5 over 10 plus a, but now for us a was e to the power of 105 minus 0.3 using the initial condition. So we just replace a by what it is for us when we give our answer. So y is a third of ln of all of 3 times 2t plus 1 to the power of 5 over 10 plus e to the power of 105 minus 3/10. One very minor comment is that this function actually works. We are allowed to go from here to here because the thing you're taking ln of is positive. One other side note is here we fought backwards to find the indefinite integral of 2t plus 1 to the power 4. Be careful, however, this worked because the inner function's derivative 2 was a constant, a number, so we could counter it by dividing by 2. But here it doesn't work like that, because when you differentiate this, unlike the 2t will not just hang around, because 2t is not a constant. Another approach, arguably a safer one, or more standard one, would be to substitute u as 2t plus 1. Go back to t then, because the guy who made this question doesn't know what u is. Or, of course, a slog solution would be to use the expansion of 2t plus 1 to the power 4.